When properly maintained, they can often deliver more than 100,000 miles of reliable service. However, when regular maintenance is neglected, failures are imminent. For example, the heat buildup caused by overflexing in an underinflated tire can cause the casing and belt packages to separate. In fact, 90% of the tire debris found on our nation's highways is caused by underinflated tires, which is the direct result of poor inflation pressure maintenance.
Fortunately, drivers are usually able to stop their vehicles safely when a tire suddenly loses air pressure. This idea that a loss of air pressure will cause a truck to spin horribly out of control, or that tire debris on the road causes thousands of accidents a year, are actually myths.
However, if a wheel comes off the vehicle, accidents are not uncommon, since the driver can lose control and the tire wheel assembly becomes a 200-pound unguided missile, which can cause serious injury or death to other motorists. Commonly referred to as wheel-offs, these accidents can be prevented by following proper wheel inspection and installation procedures.
Before we cover the procedures for installing hub-piloted and stud-piloted disc wheels, let's talk about the relationship between torque and clamping force. Simply put, torque is the force that creates rotation or twist.
In the truck tire and wheel service industry, torque is measured in foot-pounds. Regardless of the unit of measure, torque can be calculated by multiplying the applied force by the distance the force is from the center of rotation. For example, 10 pounds of force applied to a 1-foot breaker bar will generate 10 foot-pounds of torque. If the same 10 pounds of force is applied to a 2-foot breaker bar, 20 foot-pounds of torque will be generated. The application of torque to a seated fastener produces clamping force. However, the amount of clamping force generated per foot-pound of torque depends on a variety of circumstances and cannot be measured in the field.
If you guys like slick tools, here's one for you. This tool actually measures clamping force. As you'll see, the nuts and bolts must be passed through the gauge, which means the tool cannot be used on the vehicle.
The bolt acts like the stud passing through the hub. Once the nut is seated and torque is applied, the clamping force can be read on the dial. As the nut is tightened, the torque and clamping force rise steadily in a linear relationship. As the limits of bolt strength are approached, the wrench still turns the nut, but there is no additional torque or clamping force being applied. Initially, the clamping force stabilizes, then it begins to decline. Since the stud actually stretches as the fastener is tightened, continued torque will cause the fastener to weaken and eventually break. The point where the fastener begins to weaken is known as the yield point. It's important to remember that the yield point is ultimately determined by the strength of the bolt and that it can be reached without the bolt breaking. All fasteners have an optimum torque value that provides the proper amount of clamping force for the application. Whenever these values are listed as a range, such as 450 to 500 foot-pounds, always target the middle of the range to account for slight variations in torque wrench accuracy. Since proper clamping force is essential for keeping the wheels on the vehicle, and its relationship with torque is linear, the only way to approximate the correct amount of clamping force is to control the amount of torque.
Of course, just because the lugs may be tightened to the proper torque value doesn't mean that the clamping force is sufficient to keep the wheels on the vehicle. Remember, unless the appropriate steps are taken prior to tightening the fasteners, applying the correct torque will result in a clamping force that is either too little or too great for the application.
For example, paint runs, dirt, corrosion, and/or debris on wheel mating surfaces often results in a loss of clamping force after the vehicle is returned to service. This reduction in clamping force is known as joint settling. Disc wheels continually flex to some degree as they adapt to the weight of the vehicle and cargo under operating conditions. This contributes to joint settling, which is the reduction of clamping force in service. Most joint settling occurs shortly after the wheels have been installed, which is why it's important to re-torque the fasteners within the first 50 to 100 miles of service. Joint settling can be particularly severe if debris is present between the mating surfaces. When this occurs, the debris eventually works itself free, reducing the stretch of the bolt and the clamping force. Since the reduction in clamping force occurs without moving the nut, devices intended to prevent a nut from backing off cannot account for joint settling. Consequently, the first step in achieving proper clamping force is to thoroughly clean all mating surfaces with a wire brush. This procedure should be done prior to every wheel installation. The next step is to check the condition of the studs and fasteners. If the hardware is corroded, damaged, or worn, it should be repaired or replaced. Otherwise, insufficient clamping force will result. Lubrication also plays an important role in the production of clamping force. For example, hub-piloted wheel systems require 30-weight oil on the stud, as well as between the nut body and the flange. If the fasteners are installed dry on this system, more of the torque goes to overcoming friction and less to creating clamping force. This results in less clamping force holding the wheels in place, even when the correct torque is applied.
Now that you've got a handle on the basic principles regarding torque and clamping force, let's put that knowledge to work on a hub-piloted wheel system.
Hub-piloted wheel assemblies use outboard brake drums that are centered on the hub by the pilot pads. When the parking brake is not applied, the drums can shift. That's why the first step in installing hub-piloted wheels with the brakes released is to place the pilot pad in the 12 o'clock position. This will help center the brake drum on the hub when the wheels are installed. The hub also includes pilot pads for the wheels. Most dual assemblies use a series of individual pads, while some single assemblies utilize a continuous pad to center the wheel. Be sure to clean the brake drum and pads thoroughly before installing hub-piloted wheels. Once the components are clean, the hub and drum should be inspected for any cracks or damage. To prevent wheel removal problems in the future, apply a light coat of 30-weight oil or rust-inhibiting compound to the top of each pad.
Remember that the tolerance between the center hole of a hub-piloted wheel and the pilot pads is very close, which is why it's important not to over-lubricate the pilot pads. Otherwise, the excess lubricant will be squeezed out and deposited between the inner wheel and brake drum. Now, while this won't affect installation torque, it will affect the amount and rate of joint settling.
The wheel studs should also be carefully inspected. A stud that shows any signs of bending, necking, damaged threads, or threads that do not appear to be in good condition should be removed and replaced in accordance with the manufacturer's guidelines. With the hub and drum assembly properly positioned and inspected, lubricate the studs and flange nuts with 30-weight oil. Using another type of lubricant, or failing to lubricate the fasteners on hub-piloted wheels, will result in improper clamping force. In order for the installation torque to generate the correct amount of clamping force, 2 to 3 drops of 30-weight oil must be applied along the threads of each stud and between the nut body and flange. Be sure to replace the fastener if the flange does not move freely on the nut body. If the flange becomes separated from the nut body, it's best to just replace the fastener. However, the fastener can be installed temporarily until a replacement is available, as long as the flange rotates freely. Before installing the wheels, clean and inspect the mating surfaces thoroughly. If the wheels are cracked, severely pitted, or damaged in any way, they should be taken out of service. Even if the wheels are in good condition, always clean both mating surfaces with a wire brush. To prevent corrosion on the mating surfaces, some fleets use hub-piloted or stud-piloted wheel separators, which are application-specific and can be reused as long as they are not damaged. Wheel protectors designed to protect the finish during installation and removal should not be used between mating surfaces. When installing hub-piloted wheels, avoid contact with the studs by using a tire lifting bar or wheel dolly. Make sure that the hand holes are aligned and the inner and outer valve stems occupy different, preferably opposite, hand holes.
Before installing the flange nuts, make sure that both wheels are resting on the pilot pads. It's best to hand tighten the top flange nut until the outer wheel is fully seated on the pad. Also, make sure to hand tighten the nuts before applying the final torque.
Consistently achieving the proper torque on wheel fasteners cannot be attained with a standard impact wrench, since these tools are not designed to deliver controlled amounts of torque. Even torque-limiting extensions will produce inconsistent results due to variations in air pressure, airflow, and tool condition. Most 1-inch impact wrenches require 90 pounds per square inch of operating pressure, which is measured with the tool spinning freely. If the operating pressure is below 90 psi, then an impact wrench with or without a torque-limiting extension could under-torque a fastener. While pneumatic torque wrenches are gaining popularity, they are more expensive and still must rely on a steady and consistent source of compressed air. For the greatest accuracy at a reasonable cost, it's hard to beat the torque wrench for controlling and measuring installation torque. The most popular torque wrenches in the commercial tire service industry are the clicker and breakneck types. Both styles are adjustable and automatically signal the user when the desired torque has been achieved. Since clicker and breakneck torque wrenches rely on a spring-loaded mechanism, the tension on the adjustable knob should be released before storing the tool. One of the best tools for measuring torque is a dial-type torque wrench. The current torque is displayed by an indicator needle, while a memory needle retains the highest torque reading.
Dial-type torque wrenches are particularly sensitive instruments that need to be handled with extreme care. That's why the tool should always be stored in the case when not in use. Now, in the event you drop one, be sure to get it recalibrated before using it again. Digital torque wrenches are relatively new to the commercial tire industry, and like dial-type wrenches, they provide a high degree of accuracy with even greater durability.
Regardless of the type and brand of torque wrench, there are two important factors to remember. First, torque wrenches are precision instruments, so they should be treated with care. Second, every torque wrench needs to be periodically calibrated to ensure it remains accurate. This can be performed in-house with a torque tester, or the wrench can be sent to the manufacturer or a calibration laboratory. When determining your calibration program or intervals, consult your torque wrench manufacturer. Regardless of the tool you're using to apply the final torque, always start at the 12 o'clock position and snug the fasteners in a star pattern to approximately 50 foot-pounds. Never use the one-and-done approach when tightening wheel fasteners. By snugging the nuts in a star pattern, the wheels and brake drum are gradually aligned on the pilot pads, which prevents component distortion. Every flange nut should be snug before the final torque of 450 to 500 foot-pounds is applied. Before applying the final torque, carefully check the alignment of the wheels on the pilot pads. If the distance between the outer wheel and the end of the pads is not consistent, loosen the fasteners and reseat the wheels. On aluminum hub-piloted wheels, the pilot pad must extend at least halfway beyond the outer wheel. As you can see here, the outer wheel is not resting on the pad, so it is not centered on the hub. Once the inspection is complete, begin at the 12 o'clock position and apply the final torque using a star pattern. Be sure to gradually apply force at the marked load point of the wrench until the proper torque is indicated. Whenever a socket extension is used, make sure that the angle between the hub and the extension is kept at 90 degrees. Never use more than one socket extension when applying the final torque. Once all of the fasteners have been torqued in a star pattern, get into the habit of checking them one last time before returning the vehicle to service. If any of the previously torqued fasteners move before the wrench clicks or the handle relaxes, remove the fastener and carefully inspect the stud. Then replace and properly torque the flange nut.
Let me show you a cutaway of a stud-piloted wheel system. Stud-piloted wheel systems use two sets of fasteners for dual assemblies. The inner cap nut secures the inner wheel to the hub and serves as the stud for the outer cap nut, which holds the outer wheel to the inner wheel.
Since stud-piloted wheel systems use right-hand threads on the right side of the vehicle and left-hand threads on the left side, begin by inspecting the studs to make sure they are on the proper side of the vehicle.
If you find that the threads are incorrectly matched on one side or the other, it's possible that the brake drum and hub assemblies were accidentally switched. So be sure to check your thread direction before installing the wheels.
Like all wheel systems, the condition of the mating surfaces is critical to achieving the proper clamping force. That's why it's so important to clean both the hub and/or drum with a wire brush and then inspect the components for cracks or other damage. The wheel studs should also be carefully inspected. Studs that are loose in the hub or show any signs of bending, necking, damaged threads, or threads that do not appear to be in good condition should be removed and replaced in accordance with the manufacturer's guidelines. In addition, since the ball seats on the wheel play such a critical role in centering the assembly on the hub, each one must be thoroughly cleaned with a wire brush and then carefully inspected.
As long as the ball seat contour mates with the inner cap nut and mates with the outer cap nut, the wheel can be installed on the vehicle.
However, if the area between the ball seats on steel wheels is worn away to less than 1/16 of an inch or the thickness of a dime, the wheel should be removed from service. Here's a stud-piloted wheel with severely worn ball seats on one side and good ball seats on the other. Since the area between the ball seats is less than 1/16 of an inch in several places, it cannot be turned around and used as an outer wheel. When the ball seats are determined to be in good condition, the mating surfaces should be cleaned with a wire brush and carefully inspected for cracks or other damage.
Remember, on stud-piloted wheels, stress cracks can develop between the bolt holes. That's why it's important to inspect the area around the ball seats carefully and never attempt to repair a cracked or damaged wheel by welding or other means.
When installing the inner wheel, use a tire lifting bar or wheel dolly to avoid making contact with the studs. Since the inner cap nuts serve two purposes, the threads must be inspected on both the inside and outside. It's also important to check the contour of the inner cap nut to ensure it will properly mate with the ball seat. Remember, when aluminum stud-piloted wheels are installed, a longer inner cap nut with a collar must be used. When a steel inner wheel and an outer aluminum wheel are paired together on the same dual, a special inner cap nut must be used to account for the additional thickness. If a fastener is severely corroded, worn, or damaged, it must be replaced. While excessive corrosion will not affect installation torque, it will affect the clamping force. With the mating surfaces cleaned and inspected, partially thread an inner cap nut at the 12 o'clock position by hand. Ball seat wear can be significantly reduced by installing several inner cap nuts by hand to center the wheel. Using a star pattern, snug each inner cap nut to approximately 50 foot-pounds to center the wheel on the studs and seat it on the hub. The recommended torque for stud-piloted wheel systems is 450 to 500 foot-pounds dry. Therefore, lubricants and anti-seize compounds should not be used. Be sure to always use a star pattern when torquing the inner cap nuts. If a socket extension is used, make sure that the angle between the hub and the extension is 90 degrees and never use more than one extension. When installing the outer wheel, make sure the handholds are aligned and the valve stems occupy different and preferably opposite handholds. Now, carefully inspect each outer cap nut, making sure the contour of the nut will properly mate with the ball seat. Remember, stud-piloted wheels require dry torque settings, so anti-seize compounds and lubricants should never be used.
Be aware that using dry torque values on lubricated threads will result in excessive clamping force. Now, this can lead to broken or damaged studs, since less friction allows the nut to generate more clamping force at the same torque.
Once all the outer cap nuts have been started by hand, Snug the fasteners in a star pattern to approximately 50 foot-pounds to center and seat the outer wheel. To prevent marring the outer wheel, special sockets are available that fit over the cap nut without making contact with the wheel surface. Finally, apply a dry torque value of 450 to 500 foot-pounds in a star pattern, and remember to maintain a 90-degree angle between the socket extension and the hub or drum. Fastener torque should be rechecked within the first 50 to 100 miles following a wheel change. After that, rechecking torque should be performed at each regularly scheduled maintenance interval. If any fastener moves in a tightening direction when checked at the minimum torque, it should be removed and carefully inspected. If the wrench clicks or the handle relaxes without moving the nut, then the torque is at least above the minimum specification.
However, it could still be excessive. For example, if a clicker or breakneck wrench is set to 450 foot-pounds and the wrench clicks or the handle relaxes without moving the nut, then it means the torque is greater than 450 foot-pounds. If the setting on the wrench is increased to 500 foot-pounds without moving the fastener, then it means the torque is greater than 500 foot-pounds. Therefore, to find the approximate torque, the setting on the wrench must be increased incrementally until each fastener moves in a tightening direction.
To avoid over-torquing fasteners when using a clicker or breakneck wrench, always stop applying force as soon as the wrench clicks or the handle relaxes. If rotation of the fastener is continued, then an unknown amount of additional torque will be applied, which can cause the stud to yield. Dial-type or digital torque wrenches are the best tools for checking torque, since they don't require any adjustment. Not only are they faster to use, but they are more accurate than other types. When gradual force is applied to the load point of this wrench, and the user releases pressure the moment the nut moves in a tightening direction, it provides a reading of the actual torque.
Well, that concludes our program. With a firm understanding of torque, clamping force, and disc wheel installation procedures, you can be sure that the wheels you install will stay on the vehicle. And remember, when you're looking for the latest in tire and wheel training, look no further than the Tire Industry Association. For TIA, I'm Pete Bellotta. Thanks for watching.